Okay, so basically you have a graph. Let me kind of draw, I'm going to draw a real idealized picture of what that graph looks like. So you have an axis that is showing you your stress. So you have an axis on the stress side, and you have an axis which is your strain. Now you have to pay attention to the fact that the strain here is given in percents, okay? So it's not inch per inch. And the stress here, I believe, is in kips per square inch. Can anybody read that? KSI? On those two graphs out of that. Anybody have that?
Yeah, it's KSI.
Okay. So I'm going to kind of try to draw this more stylized than what it actually is. But what you got to recognize is that where this graph starts at 0, it just kind of like that. But when you get into it, it should go linear. So there's a region where it's going to go real linear. And then what'll happen is it'll start to curve. Okay. No, that's not going to work. Yeah, it kind of curves like that. Okay. So to get the modulus of elasticity for you, E, is defined as what? What is modulus of elasticity? We should know this. Nobody can tell me that? It's stress divided by strain, right? Stress divided by strain. So what you're going to do, you're going to find 2 points on this graph, one here and one somewhere down here, okay? You don't want to go down at 0 because this area is not linear, all right? You want to find where it's linear. So the best way to do that is take a straight edge and lay it next to that graph and figure out where you've got the real linear region, okay? Is everybody with me on that? Everybody know what I'm saying? Anybody out there?
Uh, I don't really know, honestly.
Are you looking at the graphs that I gave you?
Yep.
All right, so you can see that the graph is doing this, right, Jacob?
Yep.
More or less. Well, there's an area right in here where it's pretty linear. It's not going to be perfect, okay, because this is experimental, but what you're going to do is you're going to find, if you take a straight edge and lay it next to that, you can find where that's pretty perfectly linear, okay?
Okay.
What you want to do is pick 2 points, an upper point where it stops being linear and a lower point, basically where it starts. And that's going to give us what we're going to call delta strain and delta stress. So what you're going to do here is you're going to find 2 points. And what you're going to do is bring this point over here. And you're going to do the same thing down here. And then you're going to do a companion point on the stress or the strain point. So you're going to come down here, and you should actually probably draw these 2 points on your graph, just like I'm doing it, so you can read them, okay? So if I call this point A and point B, over here, I will have a stress B and a stress A, and here I'll have a strain A and a strain B value, okay? Now you have to recognize that this is in percent, okay? So you're going to have to convert percent to inch per inch. So your numbers are like 0.2%. You need to divide that by 100, okay, to get those numbers exact. Does everybody understand what I'm saying?
Yep.
You have to convert the percent on your scale to inch per inch, which is just multiplying those or dividing those numbers by 100, okay? So you're just moving your decimal place over, all right? And then to get your E value, what you would do is you would take your strain value at B minus your strain value at A, I'm sorry, stress, divided by your strain, I'll cut this reversed. Your stress value at B minus your stress value at A, divided by your strain value at B minus strain at A. And that will give you whatever value you have here. It should be in KSI. And it should be pretty close to what experimental value is. In fact, it'll almost be perfect. So if you do this properly, you should get a number for steel that's like 29 times 10 to the 6th, you know, whatever, if it's in PSI, okay? Does everybody get the idea?
Yep.
So that's step 2. You got to determine your modulus of elasticity. There's a steel sample and there's an aluminum sample. After you do that, then it asks you to compare those numbers to the published values, okay? And they give you those, okay, for steel and aluminum. And then you're kind of, they want you to kind of decide whether you're close or not, okay? All right, if you're off a lot, I'm going to tell you, you probably didn't convert this properly, or you're not reading these very well on this graph. So you have to take some time to read that properly, okay? Is everybody with me?
Yep.
Okay, so then it wants you to take and produce a what's called a yield stress. Now in your book, they show you several different ways of doing a yield stress. They have what's called the 0.2% offset, the 0.1% offset, and the 0.5% offset. I'm going to show you how to do that. You guys are going to do what's called a 0.2% offset. So let me erase some of this stuff here if I can do it. I'll just probably erase it here. So in this, what you're going to do is draw a line parallel to your modulus line. Oops, well, that wasn't good. And what you're going to do is determine what's called the yield stress. So we're doing what's called a, we're doing a 0.2% yield stress or yield point. So what you literally do is find down here on your graph where your 0.2% mark is, okay? So that's easy because it's already in that percentage. And what you do is you run a line through that point parallel to this. So what you're going to do, again, you're going to take a straight edge and figure out where you're, I'm going to try to make this, what I would do is line this up so I'm parallel with that as much as I can. Then I'm going to bring that over until I run it through that point right there. Draw a line, and where that intersects your graph, that's your yield point at the 0.2%. So to find the stress, what you're going to do is bring a line back from that point there, and that would be what we would call the yield point at 0.2%, okay? So it's important that you make sure that this is parallel here, all right? So again, you have to figure out where that linear range is. Different engineers use different definitions. One definition is the 0.1%. The other one is the 0.2, and then there's what they call a 0.5, which would be out here, and they use that just straight up, okay? And that's all explained in your book under this section, okay? Those are the two big areas that you need to work on. And I would try to do these for Thursday so that I can take a look at them with you and see if there's any questions, okay? All right, is everybody with me on that?
Yep.
Before you go putting marks down on that graph, what you might want to do is run copies of it so that if you mess them up or at least do it in pencil, so that if you do have to erase something, you can do that. So your graph is going to show me your yield point. You're going to see, I'm going to need to see this diagonal line, and I'm going to need to see that point. Then I want to see your points A and B and what you used over here for your stress and your strain, okay? So all that should be written up in that report. Okay, any questions on that?
Nope.
Okay. All right, so if that's good, we're going to shift gears then. We're going to take a look at chapter 11. Does anybody have any questions out of chapter 8 or 9 at this point? You got a chance to look at any of those problems yet? Now, we worked most of them the other day, the week before.
I think I'm good.
No, okay, all right. So if you have questions, I think one of the things we want to do first thing is on Thursday we'll talk about anything out of chapter 8, chapter 9, but we're going to focus on 11. Okay, so that's kind of what we'll be doing. So this PowerPoint, did you guys find this available? Because last week I don't think I had this available. Did you guys have that?
I got a notification at like 11:30, but I honestly didn't have a chance to look at it.
Yeah, I was still working on it. That's why this one wasn't as complete as the other one, but yeah, that's correct. So as long as it's there, it's just so long as it's open, okay? All right, so we're going to take a look at chapter 11 today, which is dealing with beams, and it's exclusively dealing with a beam type member that you would see. And we're going to look at two things, what are called shear forces and bending moments, and then kind of how they work together. So ultimately, we're going to be looking at this thing called shear moment diagrams. And as I said before, these are really, really simple once you understand the basic concepts of them. And they're a very important design tool for engineers and designers, but they will really relate to you any value of shear, what we define as shear or what we define as bending moment across a beam. And so, as I said, you'll probably see some of this in chapter 12 and 11 again, because it's such a comprehensive tool, a good way of doing things. So let me go ahead. Let me get this fired up. And like I said, I was really, really busy yesterday, and during the weekend I was out of town actually, so I didn't get a chance to develop as good a PowerPoint as I would have liked. But all of this is in chapter 11. Okay, so there's more diagrams there, and we'll refer back to those. All right, so we're going to look at just a brief introduction, talk about the types of loads on beams, and we've already really talked about this back in chapter 3. So this is nothing that you haven't seen before, but we just have to start utilizing that concept. Also, if you can't solve reactions, you're going to have a little bit of a problem with this. But these reactions on beams are pretty straightforward. But it does depend on your loads. Okay, so we'll go through some examples, make sure that everybody's up to snuff on that. Then we'll define shear forces, take a look at them, and then we'll look at bending moments, and then we'll look at them together, because it's really nice and easy to do them at one diagram. Let's say, so one of the most common structural members that you see utilized out there is what we would call a beam. And you can think of beams of many things, of course, like a floor joist is a beam, roof joists are beams basically, or at least they're modeled that way. So we do see these a lot. And obviously they're constructed from a lot of different types of materials. Steel be a very common one. Wood, if it's just like a floor joist, or then you can put things together like you could like weld a plate together with other various engineered shapes and come up with beams. Now that's when moment of inertia is going to come back into play, once we start looking at that stuff, and you'll see that back in probably chapter 12 and 13, but we won't have to deal with any of that kind of stuff right now. We're going to be strictly looking at loads, and we won't even really know anything about the depth of the beam at this point, or its shape, but we're going to be looking at loads completely. Okay, so to completely understand the behavior of a beam, you have to learn about forces that act on it. And so you have the two primary things that are acting on a beam, and then the beam has to react for that. So one is a shear force. So a shear force is a force that will try to rip that beam apart, shear it. And then bending moment is a force or a type of behavior that's going to try to bend that thing or rotate it. And then the beam has to develop a resistance to those kind of things. So we have to know, we're going to have to know things like where our maximum shear is, where our maximum moment, because those are going to be points that we're going to have to really maybe beef up, those kind of things. So beams also have different types of what you'd call applied loads. And so applied loads is anything that you're adding to the beam. Now, a beam has self-weight, which could be part of it, but a lot of times we ignore, we model it into it. But typically, we've already talked about these before. We either classify those loads as dead load or live loads. And dead load is simply a permanent load that is imposed on that beam by the structure. So for instance, the structure self-weight. In other words, the weight of the member itself or members coming into that. So you can imagine you've got a column that is pushing down on a beam. That column, if it's made out of steel, it's got quite a bit of weight to it, especially if it's, let's say, 20 feet long and it's a big section. It's going to have a lot. Things like piping, conduit, ductwork, concrete flooring, those kind of things, those would all be considered dead loads. And even a permanent piece of equipment, one that's fixed rigidly, like maybe your mechanical stuff or your HVAC, that kind of stuff that doesn't move, those are going to be all considered dead loads. And then live loads are just loads that basically move around. They instantaneously give you a load, but that's going to change. So things like people in a building, obviously we get up, we walk around, we move. That's changing. Some equipment's going to move around in furniture. Things like snow and wind loads, those are considered live loads because those are changing constantly. Like someday it was very windy. You can imagine on a high, tall building, a lot of those buildings actually sway with that. So a live load's somewhat unpredictable, and you can not necessarily get a magnitude, location, or duration. So, but they do have to be accounted for at times. And you're going to see things like if you were up north, where you do get a lot of area snow banks and whatnot, building codes are going to have snow loading built into that because that's going to be a very important function. Okay, so when we talk about beam behavior, and we've talked about this before, there are two basic types of loads that we talk about being significant, and we're going to work with these two exclusively over the next hour or so here. So we have what's called the concentrated load, or just simply referred to as a point load, and then we have uniformly distributed loads, and those come in several different types. The concentrated load just applies a force on the beam at a very specific location. So the magnitude is fixed and the direction is fixed, and so is the location. So you could have the reaction from a column or a post bearing directly on a beam, or you could even have a reaction itself. Okay, those would be examples typically of point loads. And we've talked about uniformly distributed loads. This applies that force or a portion of it over the beam. So we know kind of how to handle that. I'm going to draw some pictures here real quick to make sure we're talking about those. We know those, but things like the weight of snow on a roof spread out over the roof could be an example of a distributed load. Poured concrete flooring could be an example of a distributed load. Then you have those other types of loads we've talked about but really not used. There's a triangular load or trapezoidal or parabolic. We've never even really talked about these kind. I showed you early on in chapter 3 how to do that triangular loading. Let me just draw some quick pictures here just to make sure we're okay with what we're talking about here. So if I have a very simple beam like that, and we have point loads coming down. So if we're looking at a concentrated load simply is just showing you, we model it like this. Okay, and we're going to see a lot of these. These are going to be the two, this is going to be the one kind of thing that we're going to be dealing with. So for instance, we would have, there's a load, there's a load, there's a load. We might say that that's 10 kips, that's 20 kips, and that's 10 kips. So not only do we know its magnitude, most of the time we're going to have a direction that's vertical. We'll also know its location, 5 feet, 10 feet, 10 feet, and 3 feet. So those are examples of point loads. You guys should be pretty familiar with that at this point. So the uniformly distributed load, it looks a little different. That's my beam. Uniformly distributed load, we usually see something like this. And then what you'll see is a loading rate. And this little guy indicates that you've got that uniformly distributed load. And it'll tell you a rate such as, let's say, 3 kips per foot. That's your loading rate. And then you'll have distances like that might be 5 feet and that might be 5 feet. So we're going to be dealing with both this type of loading, the concentrated or point loading, and this type of loading, the uniformly distributed load. Now, the triangular load, and you guys remember when we talked about that, that would look something more like this. So you might have, for instance, where snow is building up, you get those little arrows that are coming down. That's an example of a triangular loading type thing. Okay, so we're not going to see, I don't think there's any examples of that in this book, but obviously engineers get into this because this is the kind of thing, like I said, snow loading could do something like this. A wind loading on a building, if we rotated this, could do something like that. Okay, so we know how to handle these, I hope, and we're going to see how this works and when we get into the shear moment stuff. Okay. Any questions so far? That should be review, hopefully. Is that good?
Yep.
All right. So a standard beam is designed to resist loads that are primarily going to be applied perpendicular to its longitudinal axis. So again, we're pretty much going to be working in the Y direction almost always, but that's not totally true, obviously. So you're going to have other things. But a beam that's going to be in equilibrium externally must also resist forces that are trying to rip it apart internally. And so this ripping type of force is referred to as a shear force. You know, just think about like bolts being sheared, which we talked about across the shear plane. Internally, what we're saying is that beam is trying to be ripped apart. If you have your book on page 332 at the bottom, Tom kind of shows you a picture of a loaded beam, and then below it he shows you an example of that thing shearing apart. So it's kind of trying to just pull it, one going down, one go up. So shear forces across the length of that beam are very important. You're going to have not one continuous shear force. It's going to change depending on where you're looking at your shear. So as you step across that beam, that shear force is going to change. And that's one of the things we're going to look at. How do we determine shear and where is its maximum? Those are kind of things. Vertical shear forces can also be accompanied by what's called a horizontal shear. So instead of just ripping one way, it can rip two ways, and then the resultant of those two can create a diagonal shear, if you will, and that can be detrimental to certain materials. So for instance, concrete is very susceptible to this, and so you can get these diagonal shear cracks. You can actually see them in concrete, which is a result of the horizontal and the vertical shear. So again, if we look at a little simple picture over here, just to kind of show you what's going on here. Let's see my screen. If I go here, what we're looking at is if you have a beam that's in shear, you're going to have shear forces that are going to be developed kind of like here. So this would be a shear force, and shear is usually denoted as V. So this would be a shear force vertically. That's going to be accompanied by a horizontal shear, a shear force horizontal. But what will happen on that increment, you're going to get potentially, well, actually, this would probably be going that way. Let me do that. If I'm looking at the way that's actually acting, it's probably getting a diagonal shear coming like this. And that can be detrimental to concrete and different types of materials. And actually, concrete will start to fail in that direction. You'll actually see stress cracks that can develop either vertically, horizontally, or diagonally, which can really rip that apart. But the one we're going to be most concerned with is this guy here, what we would call the vertical shear. So they do use that symbology V for shear, but we won't typically call it V sub V. We're just going to be talking about shear vertically. Okay, everybody kind of get the idea on that?
Yep.
Okay, so before you can proceed as a designer with a beam, you need to know magnitudes of shear across that length of it, and you have to know its location. Okay, so there's two things. You need to know where that shear is located on a beam, and you need to know what its magnitude is. So shear force is really, really simple. It is just simply the sum of all forces, either left or right, of a location that you choose. And you can essentially just say, okay, that shear at a point is just equal to the sum of the shear values left or right of your point A. And we also assign it a value of sign, negative or positive. Most people consider downward acting shear negative and upwardly acting shear positive. It really doesn't matter at the end of the day whether it's positive or negative. All we're really after is the absolute value of that shear. Okay. So we're going to take a look at a couple of examples here to show you how to do this. So let me flip back over. This is really, really simple stuff. Now, the one thing is it actually goes back to reactions. So if you can't do reactions, that's probably the hardest part. So we're going to run through something here real quick and see if we can solve this. So let's look at a beam real quick. I'm going to draw this beam here. And I'm going to draw some points on here. So let me give me a sec here. So we're going to have a reaction here and a reaction here. And we're going to strictly look at two concentrated, nice easy concentrated loads, one here and one here. So this is our load. And let's say we've got 10 kips here and 20 kips here. If you have a calculator handy, you might want to go ahead and get that out. We're going to have reactions here. And we'll say that this is 4 feet, 2 feet, and this is also 4 feet from here to here. Okay, so the first thing we would need to do is solve those reactions. So let's just do that real quick. I'm not even going to worry about horizontal reactions, so I'm just going to say the sum of, we'll call this B, and we'll call this A. So the sum of forces in Y have to equal 0. So in Y we would have reaction A plus reaction B, the way I've modeled it, has to be equal to 30. Does everybody agree with that statement right there? No problem with that? So how do we find A and B? We would just do a summation of moments. So again, this is just chapter 3 stuff that we've dealt with. So I'm going to take a moment at A, and I'm going to have 4 times 10. That's a positive rotation. And then we're going to have 6, so plus 6 times 20. And then ultimately we're going to have what? 10 minus 10, a reaction B is equal to 0. So let's see what we get. It gives us B is going to be negative 160 divided by negative 10. So we get 16 kips. And 16 minus 30 gives us 14. So over here, and here, we now can replace those values with our values. So we know that this is 14 kips acting up, and this is 16 kips. Okay, so it all starts out with that. So then, as you step across this beam, you can determine shear at any point along this left or right of a particular point. So let me clean this up, and we'll take a look at shear. You're going to see this is really pretty easy stuff. Even if you get it into, even if you get a uniform load in there, it's still pretty easy. Okay, so let's turn this off. Okay, so if I come to a point, let's just call this over here. We're going to call this, I want to know the shear here. Let's say that's 2 feet over. Okay, so the shear, and we'll just call this at A. I'm just going to call that, or we'll just call it X. So the shear at X is just the sum of the shear values left or right. So if I want to look at it going left, it's just going to be positive 14. And there's no other shear, there's no other force coming in over here. So that shear at point X is just positive 14 kips. Okay. Now, if we step over, let me erase that a minute. Let's say now we want to look at the shear here, and we'll call this Y. And let's say this distance is 4 plus 1, so let's say this is 5 feet over. Notice the distance isn't going to have a whole lot to do with it other than the location of where you're looking at shear. So the shear on the beam at that point, if I go to the left, is going to be plus 14 minus 10, and there's no other forces left if I'm looking only left. So what does that give me? It gives me a plus 4 kips of shear. Does everybody see what I'm doing? Now, if I would look right, my shear would be different than it would looking left. Okay, so you usually go either left to right across the beam or right to left across the beam. But notice that my shear started out at a value of 14 and it stepped down to a value of 4. So what that's saying is as you're traveling along this beam, the shear starting out, but it's dropping. And we're going to see exactly how this works once we get into these shear moment diagrams, because you're going to graphically be able to see what's going on at every point across your beam. Is everybody okay with that?
So you just took that 14 on the very left of the beam force up, and then
Yep.
you took the 10 kips and subtracted. That's all you do.
That's all you're doing. So what you're doing, just look at these as point loads that you're just adding, okay? And I'm arbitrarily calling up positive and down negative. I could reverse that. I could call that negative and that positive. So it doesn't matter because you're going to get the same number down here. Okay, you see that?
Yeah.
It would, on your graph, it just flips 180. So our mirror images. So if you had negative shear, I could have positive shear, but we would come up with the exact same numbers. Okay. Is that making sense?
Yeah.
So let's do one more here. Let's say we took a location. Let me erase this again. So I want to look at shear in a different plane now across this beam. And I want to come over now to this point right here, and I want to look at the shear there. We're going to call that Z. So let's say that's, we'll say that's 6, and we'll call that 8 feet over. Okay, so again, notice the distance right now has nothing to do with this. You guys see that? Other than with the location of where you are. Does everybody see that?
Yeah.
Okay, so when we do this now, the shear at Z, okay, is simply the sum of the shears, or left to right, of the point. So if we're going left, again, you have 14 up minus 10 down minus 20. And the sum of those algebraically, we have that minus 10 minus 20 gives us what?
Positives or negative 16.
Right. So notice what's happened, and this is kind of important. We'll see this here in a minute as we get into these graphs, because the graphs are going to show you everything. That's the cool thing about this. This is kind of a more laborious way of doing things. So when we do the graphing, you'll see it's real simple. But notice we went from a positive 14 to a positive 4. So you notice that the shear's dropping, right? But then when we get over here, it's actually dropped to a negative. So what's happened for that to occur, you had to go to pop from a positive shear to 0 to get to negative, right? Everybody agree with that? So you had to go from a positive through 0 to get to a negative. Everybody agree with that?
So then we technically don't have to look at the distance at all.
We don't now, but we will, Max. Okay.
Okay.
Other than, okay, when you say that, yes, technically the distance notice isn't coming into play other than it's where you're sitting. Okay.
All right.
So what that does is excludes a force right, left, or right of you. So that's where that distance comes into play. Okay.
Okay.
But it will make a difference once we start graphing it a little bit. You'll see that, okay, directly. But my point being is that we went from a positive value of shear to a negative value of shear. So in order for that to happen, we had to cross 0. Okay.
All right.
And 0 is going to be, when you cross that 0 line with shear, that's going to be a point of something important. That's going to be where you're going to experience a maximum or minimum moment. Okay. And we'll see how that goes out graphically. All right. So this is pretty simple, isn't it? Not much to it.
Nope.
All right, so let's ramp this up just a little. What we're going to do is now take a look at a uniformly distributed load. So give me a sec. Just grab a new one here. We're going to do a new beam here. So we'll do a very simple, like I said, I think you guys are going to like this because this is some of the easiest stuff we've actually done this semester. So we've got a distributed load right here, let's say, okay? And that's a uniformly distributed load. Give me a sec here to put some, so you know, you got that symbol. When you see this kind of thing, that's what's you got going on, okay? So we're gonna assume we have two reactions here, one up here and one up here. And let's see, get some distances here. Let's say this is 5 feet and this is 5 feet. And we're gonna go ahead and say that this is 400 pounds per foot. So the first thing we would need to do is model this with reactions. So we're going to, again, we'll just call this reaction A, reaction B. So remember what you're going to do is model this as a point load to just solve this thing. So we're going to take that point load would be 400 times 5. So it's a 2,000 pound load. So essentially what we're saying is that reaction A, if I'm doing a sum of forces in the y direction, notice I'm really not even looking at x or you know, the horizontal direction at this point, because even if you had a roller or a pin rather, we're not seeing any forces acting in that direction. So we're going to keep this really simple as we get to this. So we know that reaction A plus reaction B, if I take 400 times 5, the distance over which it acts, I get negative 2,000. So if by equilibrium that's 0, so all this is telling me is that A plus B has to equal 2,000. Everybody agree with that? No problem, right? So we're going to take a moment to solve the distribution, I'm going to take a moment at A. I know that some moments at any point have to equal 0. So I know that this guy's going to be acting half the distance over, so that would be 2.5 this way or 2.5 this way. So that if I'm coming from A, that would be 5 plus 2.5. So that's going to be 7.5 times 400 times 5, or we know that that's just 2,000, minus 10 for the B support. So what that gives us is 15,000. So we get B is a negative 15,000 divided by a negative 10. So that gets 1,500 at that support. 1,500 minus 2,000 gives us 500. So we know that A is 500, B is 1,500. So again, all of this goes back to reactions and that kind of stuff. And then we'll see how this works on this one. So that's 1,500 and that's 500. Hopefully that's not a problem for anybody, okay? I'm going to go ahead and delete that. And delete that. So you're going to always start out with reactions, okay? Again, if you can't solve reactions, you can't solve anything, all right? All right, so let's step across this beam, and we'll take a point here. We're just going to say that's half the distance over. That's 2.5. We'll just call that point A. So if you have that at point A, what you're looking at, the shear at A, who can tell me what we're going to have there? If we're looking to the left, what's the shear at A going to be? Well, there's only one force out here, right? 500?
500?
Yep, so it's going to be a plus 500 if I assume up. So that would be 500 pounds. So the shear at point A is 500 pounds. And I want you to notice, actually, as you step across this beam, the shear is 500, 500, 500, 500 until you get to here. Okay? Does everybody see what I'm saying? As I step across, nothing's changing. So it's always going to be 500. Now, when we get over into here, that's going to change a little bit. Okay? So what we're going to have, let's say we're here now at B, and let's say we're over 2.5 feet. So the shear at B is going to be a plus 500, and then this is acting down at 2.5 times my loading rate of 400. Okay, because I'm going over 2.5 feet at a loading rate of 400 pounds per foot. So the total amount of shear here is based on that distance times that loading rate. So let's see what we come up with here. We got 500 up minus 2.5 times 400. So what'd you guys come up with? Anybody get a number?
Positive 500?
I got a negative.
Same.
Yeah,
Okay.
negative.
So again, remember, the sign's not critical as long as you're consistent, okay? Up, down, all right? So notice what's happened now again. As we step across this thing, it's staying constant. That shear is staying constant at 500, but once you start getting into this, it's going to start doing what? It's going to start dropping. And the further you get across this thing, the more this distance or that distance is going to increase. So this number is going to get bigger and bigger. Eventually, you'll see it would come up to negative 1,500, and then that'll push it back up. So this is how you're calculating shear. It's not real instructive though, because it's not really showing us everything that's happening along this beam at every point. So we're going to see that's where the shear moment diagram is going to come in, because that's going to show us directly. We're going to still use the same principles, but we're going to see it a lot cleaner. Okay, is everybody okay with that so far?
Yeah.
Okay, pretty simple, isn't it? Not much to it. So let's go back. Let's go back into here, and we'll talk about something else now. Okay, so all we're doing is this equation. The shear at any point is the sum of shears left or right off of that point. Okay, and again, we usually walk across the beam left or right. Again, that doesn't matter, but do keep in mind the shear at the same point, left or right, is going to be different. Okay, because your loading is going to be different left and right, unless you have a symmetric situation. That would be the only time it's not. Okay, and that may not always be true. All right, so in addition to your shear forces that develop in beams, bending will also be something that has to be considered, because it's going to be something that's going to try to fail that beam as well. So bending moments are caused by loads on a beam as a moment, which is a product, remember, of a force times a distance. So remember, go back to that concept of moment. It's just a force and a perpendicular distance. And so we just used that when we solved reactions, but we're going to see how that works in the beam. So bending moments occur simultaneous with shear forces, but they're going to give you a totally different type of failure mode. So remember, shear wants to rip that beam apart, where moment's going to want to bend that thing along its axis. And you can either call it rotating that beam or deflecting it. And deflecting is probably a little bit easier to see, because what that's trying to do is try to move that beam either up or down. So what I'm saying here by that concept of deflection, let's go back to this. If we look at this, I'll try to do this the best I can. It's a little hard to draw with this, but if we have a normally supported beam like this, and you've got this thing supported simply by, you've got a reaction here and a reaction here, and let's just say we've got some concentrated load of force here. What moment's going to try to do to this thing is bend it like this, right? And this amount here is referred to as deflection. And if that deflection gets too severe, it could fail your beam. And then you've got the other fact there going on is you have shear going on simultaneously. So the two things are one's trying to rip the beam apart, one's trying to deflect it and bend it or rotate it. You guys have all experienced deflection, I'm sure. Have you ever been on a bridge and let's say you're on a stop location on that bridge, you can actually feel the bridge go up and down. Anybody ever experience that on a bridge where it deflects like that?
Yeah.
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 And deflection, there are certain amounts of deflection that are legal, if you will. In other words, they're built into the system. So we recognize that you cannot get rid of deflection. The only way you can really do it is support it more often. And of course, then it becomes a trade-off in cost and that kind of stuff. So deflection is allowed. We have what's called allowable deflection, but if the deflection gets too much, then you got a problem. Okay, and we'll talk a little bit more about deflection. I think we get to that in chapter 12 and 13. So, but that's what we're looking at. We're looking at that concept of that deflection, that rotation. So that bending moment's going to try to rotate that beam, and if it's too much, then it could collapse. So from a design standpoint, it's important to determine magnitudes and the distribution of the bending. And what we're really looking for typically on bending moment is the maximum point of moment or the minimum point, but maximums are more important because that's going to be where your design concepts kick in, okay? So to determine that magnitude and the location, that's critical because you need that to properly size a beam. So this kind of will start to get back into moment of inertia, because remember, moment of inertia is the thing that resists that bending. Okay, so that's the property of the area of a beam that could resist bending. So if you were using an I-beam, let's think about this, and the bending was a certain amount of bending, and you didn't want it to be that amount of bending, what could you do to increase that moment of inertia for an I-beam? Anybody remember? Just think about that. What would increase the moment of inertia that might size that beam so that they don't have as much deflection? How do you increase moment of inertia on an I-beam?
Make it thicker.
Thicker which way?
Honestly don't know.
Basically, Jacob, if you just increase the depth, okay, the distance from the flange to flange, that, if you look at those charts, that will directly increase your moment of inertia.
So make it taller, basically.
Yes, exactly. Okay. So when we talk about selection of proper beam size, what we're looking at is how does that play out with moment of inertia, essentially. Okay, and we'll see that will directly come back in chapter 12. So then the other thing is you might have to determine, because I got a maximum moment at some point, I might need to put some kind of lateral bracing in. That's the place where I would tend to want to put that lateral bracing. Or if you're going to take two members and splice them together, you don't want to put the splice at the point of maximum moment, because it's going to have a tendency to rip it easier. So you would want that splice someplace away, or even a point at minimum moment. So that's why bending moment is going to become really, really important. So bending moment is just simply defined at any location on the beam as the sum of moments either left or right of that point. So again, all you're going to do is do a simple moment equation. You know, it's just a force times a distance, and we can determine what that point of maximum bending moment is for those values. Again, we'd have to look at simple beams, solving their reactions, and then doing a moment. So again, now moment, remember, is just a force times a distance. And if you're using distributed loads, you're going to have to think about that a little bit differently, because you're going to have to calculate the point that you're dealing with and then where that thing is located. So we'll take a look at a simple example. And bending moment, by the way, this, I didn't put that on here, but the signs are arbitrary. As long as you're consistent, you're good. So remember, we usually say clockwise, a clockwise moment is positive and a counterclockwise is negative. Okay, that's just real standard, but doesn't have to be that way. So we're going to take a look at a couple quick examples here, and then we're going to do, the last thing we're going to look at is doing the shear moment diagram. So let me flip over here real quick, and we'll spend the rest of the time looking at shear moment diagrams. They're actually real easy to do. I don't know, they're going to be easy for me to draw. All right, let me back this up. We're going to look at that beam we just looked at before. I'm going to just draw a real simple beam again. Give me a sec. And this is all in Tom's book on that chapter too. So you can go through that, and you'll be able to see what we're doing here. It's real simple stuff. We put a reaction here. We already solved this reaction, but we're going to just draw this again. Going to have a reaction load here, and a load here. Just give me a sec of this. Okay, so we're going to have, I think we had 14 kips on this side and 16 kips on this side. So we've already solved this beam. And we know that this is 4 feet, 2 feet, and 4 feet. Okay, so now we're looking at solving a moment. So now distance is pretty critical when you're solving a moment. So let's say I'm kind of solving a moment right here, and we'll call this like at A, and that point A is 2 feet over. So if you're looking at the moments left, you're just looking at this force times that distance. But if you're looking at the moments right, then you're going to have that force, and that force, and those distances are going to be more involved. Okay. So we're going to go to the left. We're going to say the moment at A. We're just looking at the moment, not the sum, but really you are doing a summation, but I'm just looking at the moment at A. It's just going to be the sum of those moments. So this one would just be simply 2 times 14, and I'm going to consider that a clockwise moment. So that would give us what? Positive.
28.
Sorry, what was that?
28.
Positive 28, right?
Yeah.
Because we're defining that as a clockwise moment. And what would the unit on that be? Now remember, moments are what? Force times the distance? So that would be what? Kip feet? Kip feet. So shear is going to be just strictly the load force value, pounds, kips, newtons, and moments are going to be a force times a distance always. Okay, so just keep that in mind. All right, so let's come over here and do another moment now. We'll do a moment here. We'll call this moment at B. Let me erase this. And we're going to come over, let's see. Let's come over 5 feet. Okay. So what we're going to have now is the moment at B is just the sum of those moments either left or right of that point. So the first one, if I look at, this is going to be what? 5 times 14, that's a plus moment, plus 5 feet times 14 kips. Everybody agree with that?
Yeah.
So then if I look at this one, if this is 5 and that's 4, this distance right here is 1 foot, correct? And it's tending to turn the beam counterclockwise, so that's going to be a -1 times 10, and that would be my moment at that point, looking to the left. So remember, if I'm looking right, it would be different. So let's see what we come up with here. So we have 5 times 14 minus 10. So that gives us a plus 60, and that would be kip feet. All right, you guys get any idea there? We'll do one. We'll do one more. Let's come over. I'm going to go ahead and erase this. We're going to do one more section. We're going to call this C. We're going to come over 2 feet this way. So we're going to have 2 plus 2 plus 4. This will be 8 feet total. So we're going to be 8 feet total. And that into C. So the moment at C is going to be 8 times 14, positive rotation, 8 times 14. And then we're going to have 2 plus 2. So that's going to be 4 to that 8, or that 10 kip load, but that's acting counterclockwise. So that's going to be, what do we say, 4 times 10. Okay, again, that's 2 times, or plus 2. And then we're going to have the 20 kip load, which is 2 feet over, and that's also acting down. And so that'll give me that moment. See what you guys come up with. I got a positive 32. Does anybody agree with that? Kip feet. Anybody get a positive 32?
You said positive 32?
Yes.
Yes, I did.
Okay, good. So let me ask you this. Where is the point of maximum moment? A, B, or C?
C.
Point of maximum moment. Which is the highest number? A, B, or C?
B.
B is right. But here's the thing about that. Remember, we're looking for maximum moment, but the problem is that this may not be exactly maximum moment, because if we step this way or that way a little bit, that actually might max out a little bit more. So this method is not very good, because if you don't pick the exact point of maximum moment, you're not getting it. So this is another reason we're not going to want to do this method. This method's just kind of sloppy. And it's also not going to give you the total picture. So we're going to shift gears and get into what's called a shear moment diagram, which is going to give us values of shear across that beam as a graphical solution completely, and we're going to also have values of moment, and those will be displayed very nicely. So let's go back to the PowerPoints, go through those a little bit, and I'm going to run some problems on you doing this stuff with you. And this is really easy stuff, great stuff. So what we're going to do is combine these two things into what's called a diagram. And we're going to do both a shear and a moment diagram. Now, the way Tom kind of explains it, he shows you shear diagrams first and the moment diagrams, but we normally draw them together and we call it a shear moment, or shear. Some people just call them shear moment, but it's really a shear and a bending moment diagram. So this is an awesome technique. It's going to be used to calculate your shear and bending moments. It's much easier to do. It shows your maximum moment of shear and maximum across, actually not just maximum moment, it shows you any value of shear across that beam from left to right. And you can easily pick out where your maximum shear is, and also the same is true with moment. It allows you to step across that beam and see the moment at any point on that beam very easily, and particularly looking at pinpointing maximum values. Okay, so a shear diagram, it's just a graphical illustration of your shear forces. And your shear diagram is typically, or I mean, I would say almost always drawn below the free body diagram of the beam. And it's going to visually describe exactly what's happening with that shear as the forces vary across it. The moment diagram then is drawn right below the shear diagram. And we utilize the shear diagram to generate moment. So the beauty on doing moment diagrams is you don't even have to calculate distances times length or forces and all that stuff. You just simply use the area under the shear curve to determine your moment. So that's going to be really, really nice once we get into that. So shear diagrams shown directly beneath. Concentrated loads are going to either increase or decrease the shear force at a particular location by the amount of force that's being applied. So this is going to indicate that as your shear diagram moves vertically under the influence of those concentrated loads, you're going to see how that works. So uniformly distributed loads, they're going to change the shear force in a uniform rate. And they're going to be based on the intensity of that load. So what you're going to get with that type of loading, you're going to get a slope line or a diagonal line. And that's going to be equal to the intensity of the load, which is essentially the slope rate. So basically, we'll be taking the slope rate times the horizontal distance, and that's going to determine our intensity, if you will. Okay. So I'm going to generate a shear diagram first. Then we're going to come back and look at moment and shear together, okay? So shear diagrams are really the key. And of course, actually the free body. If you can't do the free body, you can't do any of this, okay? So I'm going to look at a couple of examples with you, and I'm going to do, there's examples 3, 4, and 5 in your book. I'm going to I'll probably just do a couple of those real quick, and then we'll jump over to do a shear moment diagram, okay? So give me a sec here. And we're going to be doing a lot of these things on Thursday. So, but I will say you want to try to do a lot of this homework as much as you can. It does help if you have a straight edge when you do these things. I like a straight edge and I like a scale, and I also sometimes will use a French curve because you're going to see when we get into moments they're going to have some kind of strange increases and decreases. All right, so let's draw this diagram. So I'm going to have actually, I don't have a lot of room, so what I'm going to do is just draw a very simplistic beam. Okay, so I'm going to have my beam here, and we're going to have forces on this thing. So we're going to start from scratch on this. We know that we have a reaction over here, and we have a reaction over here. And we're going to have an applied load here and an applied load here. Okay, so let me do something here. This is going to be a reaction. This is going to be a reaction. This is going to be a load, and this is going to be a load. So this is going to be 20 kilonewtons. This is going to be 5 kilonewtons. That's our load. We're going to know that this is 4 meters, 6 meters, and 2 meters. Okay. Now, here's what I always do with a shear. I'm going to do my shear diagram right below this. And with the shear, wherever you have a concentrated load, you're going to have a point of a line that's going to be critical. I call this a critical line. So I'm going to go ahead and put my critical lines in right now. I have a critical line at the reaction. I have a critical line at the point load here. I have another critical line. So notice I'm just dropping those lines vertically straight down. And I'm going to have another one here. Okay. So we're going to see where those come into play in a minute. So the first thing we need to do is solve reactions here. Okay. So we got reaction A over on this side. And we have reaction B on this side. Okay. So we're going to assume nothing's happening horizontal, so we're just going to assume we have a 0 happening in the horizontal. So we've got sum of forces in Y. We have A plus B, and then we've got minus 25, so that's going to equal 25. Everybody agree with that? So far, we're good? Okay. So I'm going to take a moment. I'm going to take a moment at A. By equilibrium, I know that's 0. I'm going to define clockwise moments as positive. So we start here. I got 4 meters times 5 kips. That's a positively acting moment. Then we have 20 kips times 10. So that's also a positively acting moment. So 10 times 20. And then this is what, 12 meters? And that would be a negative rotation. So there's my moment. Let's see if you guys agree with that. Let's see what happens and see what numbers we generate there. So I'm getting B, reaction B is going to be a negative 220 divided by a negative 12. Looks like 18.3. Call that 3.3. That's kilonewtons acting up. Is everybody getting that number?
Yep.
So A is going to be what? 6.33 acting up kilonewtons. Everybody got that?
That 25, that wouldn't be negative.
Well, it was, Jacob, on this side of the equation, but when I bring it over, it's positive.
Okay.
Makes sense now?
Yep.
Okay. All right, so we're almost ready. So what I'm going to do is I'm going to go replace the reactions with their values. So this is 18. It should have thin. Let me try that again. 18.33 kilonewtons up, and this is 6.33. Okay. Here's the cool thing about this other thing graphically. If you blow reactions, the shear diagram is going to tell you that. I'll show you why, because it won't resolve to zero. Okay, so it's kind of like doing the joint problems. If everything doesn't resolve to zero, you got a problem in your reaction. Well, it's going to happen the same way with our diagram here. Okay. All right, so this is my free body up here. And remember, I drew these things, I call these critical lines. There's critical lines happening along your point values, okay? So underneath this, we're going to start to construct the shear diagram. So this is where a straight edge and a scale is really nice. It really helps. I'm going to put my shear right here. So this is my shear, and that line represents a point of zero shear. So above it was going to be positive shear. Below that line is going to be negative shear. Is everybody with me? All right, so watch how easy this is. So remember, the definition of shear is just the amount, the sum of shear left or right as a point. We're going to start at this point and we're going to step across, okay? So I'm going to start at this point. Let me see if I can change color on this one. Maybe that'll help. Okay. So my shear is just equal to 6.33. So I'm going to draw my shear at 6.33. And I'm going to label it. Oh, I don't know if I want to. Well, I guess I can. Yeah, I'm still in that mode. 6.33 plus. So that's the amount of shear at that point. Does everybody see what I did? That's because my reaction is 6.33, the shear, all right? Now, as I step across here, that shear is going to stay the same until I get to that critical line. So what I'm going to do here is I'm going to draw my line as a constant line right there. All right. So now we get to the shear at this point. We'll just call that shear at A. Yeah, let's call it A, not B. So let's start out. We started out with a shear. We'll just call that shear. We started out with at A is a positive 6.33. Now we're going to call that shear B. So the shear at that point is going to be plus 6.33 minus that amount of shear, which is 5. So we have 6.33 minus 5. It gets us an amount of shear at 1.33. So it stayed the same until it got here, and then this is going to drop drastically. And that's going to drop drastically down to 1.33. So everybody see what I'm doing? So now I know that the shear along this point, nothing's changing. So that line stays constant until I get to that point. Because notice if I put up here, nothing's changing between those two until I get over to here, and we'll call that the shear at C. Now what we have is the shear at B, or you can say ABC. We got 633 minus 5, and now I'm going to say minus 20. So now I get 18. Oops. Oh, you know what I did, guys? This isn't 633. That's 67. Let me change that real quick. I just noticed when I did my subtraction, I did it wrong. This should be 667. Just change that in your. That's going to change this a little bit. Sorry about that. No one caught that, huh? Let me change these numbers up here. I just had a little bit of a mistake when I had my math here, so. So that's 6, 7. That's 6, 7. There we go. Okay. All right. So this should be 18.33. So what's going to happen now, if we look at the shear at this point, it's going to drop down below to that point, which is going to be 18.33. And as we step across on that beam, that's going to stay the same at 18.33 until we get to the end point there, which we could call the point of D. And you're going to have minus 18.33 plus 18.33, which is this guy pushing it back up. So what do you notice about this shear diagram? It starts at a value, but it has to end back at 0. If it doesn't end back at 0, if this doesn't equal that, you got a problem. And mine didn't because I had a mess up here. I apologize for that. Okay. So we just start out with that. We keep it constant. When we hit that load, it drops, and then you keep it constant. You hit that load, it drops, keep it constant, and then notice the reaction just pushes it right back up. Are you guys seeing how that works?
Yeah.
Where's the point of maximum shear here? It's kind of a loaded
BC.
Well, yeah, but if you look at that, Jacob, it's kind of a loaded question. There is no point of maximum moment because look at this. This whole range of the beam stays at what? It stays the same, right? So there's no point of maximum moment. What there is a range of maximum moment. I mean shear. I apologize. Maximum shear, okay? There is no point of maximum. You don't typically get a max point in shear. You usually get a range of values.
That
Does that make sense now?
yeah, but that VC and the to the right where you did calculation, should that be negative 18.33?
It should be.
Okay.
Yeah, sorry about that.
And would it be VA then?
VA.
Because that's the highest one.
Well, no. Remember, we don't look at the sign, okay? You look at the absolute value. Okay.
Okay.
So this is the point of maximum shear. Actually, it's the value of maximum shear. So you would call shear max, but you would just, it's 18.33. That's it. Okay. Does that make sense?
Yep.
Now, notice at this point that it crosses the zero. So when we get into the moment, which we'll get here in a minute, that's going to be a critical point because that's going to define where you get a point of maximum moment, okay? So keep that in mind. Where shear crosses zero, you're going to get a point of maximum moment. Let me do another one. I'll try not to screw up the the reactions for you. I just had that little bit in there, but that would not have closed back to zero. That's why I caught that at first. So the cool thing is with these guys, if you don't do that right, they will not go back to zero. Okay, so let me see if I can get this back here. Give me a sec. We're gonna do another one real quick. Okay, so we're going to have one a little bit more convoluted. These are going to get really easy. You're just going to have to do a couple of them and see. Hopefully, I'm trying to make it as simple as possible for you. So we're going to have a beam here, and it's going to have a concentrated load right in the middle, but it's also going to have two uniformly distributed loads. So we're going to see how those work. Okay, so this is going to be a reaction here. This is going to be a reaction here. And I'm going to put two uniformly distributed loads here. One right here and one right here. Okay. And we're going to have loading rates on those guys. Let's see. This guy's going down and these guys are going down as well. They could go up, by the way. So that could impact what you're doing. So we're going to have 10 kips here. This one is going to be 1 kip per foot. This one is going to be a load rate of 2 kips per foot. And we're going to give you the reactions, so we'll just step through that. Okay, so this is going to come out to be 17 kips, and this turns out to be 22.5 kips. Okay, so there's our load diagram and our free body. So we have uniformly distributed load. Oh, by the way, this is 10 feet here and 10 feet here. So we have 2 kip per foot loading here, 1 kip per foot loading here, and then we have a concentrated load. So here's the first thing you want to do. You want to generate, again, what I call critical lines. Going to be a critical line here at a reaction, critical line at a concentrated load, critical line at another reaction. Now, these guys would generate a critical load at their endpoints, but the endpoints happen to be touching at the same point as a concentrated load. So right now we only have 3 critical lines. Okay, is everybody with me? So we're going to start out drawing our zero shear line. That's my zero shear. Zero shear. This is going to be positive shear. This is going to be negative shear. Okay. And I'm going to generate this thing left to right again. So I'm going to start out with that right there. Okay. So we start out, the amount of shear here, okay, is going to be 22 going up. So we have 22 going up. So we can label that. That's a plus 22.5. And the value of that would be kips. Okay. Is everybody okay with that? So now what's happening here is as you step across this beam, the shear is increasing. Okay, so what it's going to do is generate a diagonal line. So from the shear point, if that's shear at A, if you call that point A essentially, if you're calling that A, it's a plus 22.5. At shear B, if we're just to the left of this point, so we're not taking that load into consideration, then the shear at that point B is going to be plus 22.5 minus 10 feet times 2 kips per foot. So what this is doing, that's my load rate times my distance, my load rate times my distance, and it's minus because they're all acting down. So when we get that, we get 10 times 2 is 20 minus that from the 22.5. So this gives us a plus 2.5. Everybody see that? So what that has done at this point is it's giving me a diagonal line like that. And this value here is plus 2.5. So the minute we step over into that 10 kip load, it's going to add another 10 kips down. So basically we would say it's going to be the shear at B minus 10. So 2.5 minus 10, what does that give us? What'd you get?
Negative 7.5.
Right. And the unit on that would be what? Kips, right? So
Yeah.
all of these are in unit of whatever the force is, okay? So on our diagram, what we simply do now, and again, if you use a scale, it's kind of cool if you use a scale because you can generate these pretty nice pictures. So we're coming down now like that, and we would label that minus 7.5. Now, if we call this D, that's going to be equal to the shear of C plus another, well, actually it's negative if you want to think of it that way. It's actually minus 10 times 1 kip per foot. Okay, so 7.5 minus plus a minus 10 gives us a minus 17.5 kips. So we would plot that, and that slope rate is flatter than this one. So if you did this graphically, you would see it's a lot flatter. That brings me to here, and that gives me negative 17.5. But in order for this to be correct, it has to go back to 0. So notice that's going to be a positive, that's going to be a negative. So whatever you're calling that point, you're just going to take the shear at that last point plus 17.5. If that doesn't equal 0, you got a problem, which ours does. So we're good at that point. Okay. So look at this diagram. What this diagram is showing is that you step across this beam, I can tell you exactly what's happening at any point along that beam in terms of the shear. And that diagram just gives me all of that. Here's the other thing. Where's the point of maximum shear? This one actually does have a point of maximum shear. Who can tell me where the point of maximum shear is?
D.
No. You're saying this? Isn't 22 higher than 17?
Yeah.
Okay, so this actually does have a point of maximum shear. It happens to occur right at the reaction, okay? So sometimes you don't have sometimes you have a range of maximum values for the shear, and sometimes you have a point. And this one specifically has a point. I want you to notice this too. See that? It's crossing 0. On the moment diagram, that's going to give us a point of maximum moment, okay? Gives us maximum moment. You guys get any idea?
Yeah, but like on the last one, I thought you said it was the highest number no matter the positive or negative.
It is. Isn't that the highest number?
Oh, yeah, never mind.
Okay.
Never mind.
Yeah, don't worry about the sign, Jacob. Just look at the absolute value. Okay.
All right, yeah.
Sign has nothing to do with it. But even so, it's 22 is still greater than 17.
Yeah, no, I see it now. I don't know why.
I know it's easy. It's easy to get messed up, trust me. Okay. All right, so we're going to take now, and what we're going to do is combine things, okay, and show you how to do what's called a shear moment diagram. And and this is actually pretty easy as well. So let me, I'm going to clean this screen. Well, I'll tell you what, we're going to flip back over. Let's take a look at the last section here. So what we looked at was on this shear diagram, we're constructing that beneath the free body. So the concentrated loads directly increase or decrease that shear force by just addition, okay? And so they move it vertically up or down. A distributed load, notice, is it puts it at a rate of intensity. And so you get typically a diagonal line that's going to happen, either up or down, all right? So I think we did problems 11.3. I did 11.3 with you and 11.5. So if you want to look at any others, we're going to do a lot of these on Thursday too. So if you're not quite catching it yet, what I want you to do is make sure you try these for homework, and then we'll go over a bunch of them on Thursday. And you'll see after you do a bunch, you get the idea. So let's look at the bending moment diagram. So the bending moment diagram is shown directly beneath the shear diagram. I'm going to have a little bit of tough time putting these in there. So I'll try to do the best I can. So the bending moment at any point along that beam can be found just simply by summing areas contained under the shear diagram. So that's the beauty. You don't have to go through that distance times the force kind of concept and figure out a moment and add them together. All you got to do is just add areas together. So you just take the individual areas under the shear diagram, and then you algebraically add those together, and you can find the bending moment at any point, or you can also graph it, which gives you the total solution. All right. So here's some key points to remember with your bending moment. That the bending moment always starts at 0 and it has to end at 0. Okay. Now, if your shear moment diagram is correct, then this always has to be true, okay? If your shear moment diagram is off, then you're gonna have this will never be true. But if your shear moment diagram is not going back to 0 at the end, then you got a problem with your reactions, okay? But bending moments always start at 0, they always end at 0. The location of 0 shear is gonna give you a maximum or minimum moment, okay? So that's gonna be a critical point. And you can actually have several points where that zeroes out. So you might have like a local max and then a high max, a total max. So rectangular areas, and this will be a little tough, and I'll go through this with you guys on the board on Thursday, but rectangular areas under your shear diagrams translate to straight diagonal lines, okay? So on your shear moment diagram, if you got a rectangular area, you're getting a straight line up or a straight line down kind of thing. That slope depends on the magnitude of the area, so as the area gets bigger, the slope will get steeper, basically. For non-rectangular areas, such as trapezoids or triangles, those areas translate into parabolic curves. They're curved lines. And that's the hardest thing. You need to kind of decide whether that parabola is increasing or decreasing. So I got a little cheat sheet I'm going to make up for you guys on, I'll give that to you on Thursday. I didn't have time to draw it up on CAD for you, but I will get that done and give that out to you. Okay? So we're going to take a look at this process and show you how easy this is to do. So let me go back to our whiteboard. So what we're saying right now is to solve the moment diagram of this, it's pretty simple because I have an area right here and I have an area right here. But this area is what you call a trapezoid, okay? So I could solve the area under here pretty simply. Anybody know how to solve the area of a trapezoid? Nobody knows the area of a trapezoid? Nobody knows the area of a trapezoid. All right. Well, if you took that value, so that area 1 would very simply be equal to 22.5 plus 2.5 divided by 2. That's the average height times the distance over which that perpendicular is acting. Let's see what we get. Anybody get a number for me? Check this, guys. I got a positive 281.25. So I'm taking 22.5 plus 2.5. Oops, I think I blew that. Hold on a minute. Yeah, I think I did. That number doesn't look right. Let me check that. I get a totally different number now. That was 125 sound. Anybody getting that number?
125?
Yeah.
Yeah.
Okay. 125, what would the unit on that be? Well, this would be kips, right? Right here, kips times a distance of feet. So this would be kip feet. And shouldn't that be the unit for a moment?
Yeah.
Okay, so we're just gonna do a real quick moment diagram under here just to show you how this all works out. So if I put my moment diagram here, this is my point of moment. That's my line of moment. So this is my, let me do something. I'm gonna bring these lines down a little bit. So this would be considered my 0 moment line. And this is my 0 shear. Okay. So remember what we said, that moment's gonna start at 0. What it's telling me is it's peaking right here at 125 because that's a point of maximum. shear or 0 shear. What's really weird about this is going to be a parabola that's going to open up like this. Okay, it's going to max out. So then the area of 2, we're going to have the area final is going to be the area of 1 plus the area of 2. This guy has to go back down to 0, okay? Because it has to start at 0 and it has to end at 0. So the area of 1 is 125. We're going to add to that negative 7.5 minus 17.5 divided by 2 times also 10. If that doesn't equal 0, we've got a problem. So when I do this trapezoidal area here, that area becomes a negative trapezoid, gives you negative 125. 125 minus 125 equals 0. And what you get is you get this parabola that's going to be going like that. Okay, so this is my moment diagram. It peaks right here. So with this, we know exactly where the point of maximum moment is and what its value is. Okay. Did everybody see that?
Yeah.
Okay, so I'm gonna, it's hard for me. Let me see, I've got some different, I'm gonna do one from scratch, okay? So that we'll do the shear we'll develop the shear diagram and the moment diagram together, okay? So give me a second here. We'll do an easy one and then we'll build up to another one. So let me erase this. You will see as you do these, this is really pretty simple stuff. Okay, and that's the beauty of it. It's really nice to be able to have something that's not so hard. Oh, come on, give me that. All right, so we're gonna do a really simple beam, simply supported. It's really hard on this. I thought I would really have a little bit more room on this, but I just don't have the room that I want. All right, let's see. We're gonna have 2 reactions. One here, one here, and we're gonna have 1 load right here. Okay, so here's our load, 2,000 pounds. Here's our reaction, and here's our other reaction. We know that we have 4 feet and 6 feet. Okay. Let's go ahead and we'll solve the reactions real quick, A and B. I'll tell you what, I'm just going to give them to you for time purposes, but you should be able to solve those reactions. But this reaction at B turns out to be 800 pounds. So this is in pounds. And the reaction at A is 1,200 pounds. So we're going to want to develop the shear moment diagram. So we're going to do the shear first. We're going to do the moment secondarily. So the first thing I want to do is develop critical lines, because those are going to be useful both in terms of the shear and the moment. So I'm going to have a critical line here. Where else will I have a critical line? Any place else?
2,000 pounds.
Okay, right, at the concentrated loads, right? Any concentrated load is going to give you a critical line. So go ahead and just put them in because you're going to use them, okay? And any reaction typically is going to give you a critical line. So if you start out with doing that very first thing, you won't have any problems when you get into these. So we're going to start out with shear first. We're going to develop the shear first. Let's go ahead and put that in a little bit darker line. And I'm going to then develop from that, I'm going to develop the moment. So I'm going to probably run out of room, maybe not. So this is going to be my shear, and this is going to be my moment. And this would be the 0 and the 0 line of both, okay? Has everybody got that? So let's change the color here. So we start out with the shear. What'll the shear be at this point right here? What's this shear going to give us?
Would it just be 1200?
It will be. Okay, so it's simply just what your reaction is in this case. So in this case, it's going to be 1200. So I'm going to label that. Now, what happens to that shear as you step across the beam? What happens to that shear as we step across?
Decrease?
It does nothing. It stays the same. It stays constant all the way until you get to there. Because there's nothing going on down here up or down that influence that. Does everybody see that? Not changing. But when we hit this, what's going to happen to that shear? You're going to have shear that's going to be equal, if we call that point A, you're going to go 1200 minus what?
2000.
2000. So at that point, it instantaneously drops. So we have 1200 minus 2000. Gives us what?
Negative 800.
Yeah, negative 800 shear. And of course, that would be
In
pounds.
that 4-foot area, is there no force at all?
Say that again now?
In the 4-foot like length right there, there's
Yep.
no force that's acting down.
Correct. So there's no force in here, right?
Yeah.
So the shear can't be changing either.
Okay.
But so what's happening is you're starting out with a shear of 1,200 pounds, and it's remaining constant. That's what's happening here, okay? Now, when we hit this, it instantaneously drops. You get that now?
Okay. Yeah, I understand that.
Okay. That's really, really important. But, you know, once you get this under your belt, this is it, guys. It really doesn't get any harder than this. All right, so that on our diagram, sorry, guys. On our diagram, what we're saying is we now have negative 800 here. Okay. So also, that means that this shear is staying what? The same, because there's no influencing force in there, right? So on our diagram, we're going to draw this guy constant. And when we hit this last point, it has to go back to 0, right? Well, if we look at this, the shear, we call that point B, is minus 800 plus what?
Positive 800.
And that takes us back to 0. So that does two things. That validates my diagram, and it validates my reactions. Okay, everything's good at that point. All right, you guys see that?
Yep.
All right, so we have now two areas to consider, area 1 and area 2. Now, since these are just rectangular areas, it's going to be a really simple moment. I think I'm going to move my moment. Give me a sec here. Let's take this guy and move him a little bit. So I have more room. So my moment, because I've got that real simple area, the moment's going to be pretty simple too to deal with. Let's see. I'm going to move my moment down a little bit. Go back to my color here. So this is going to be the reference line for 0 moment. Moment. So, oops, give me the color I wanted it to. I'll just keep it there. All right. So moment is just the area under the curve. So the moment, remember the moment has to start at 0, right? And this is going through the 0 reference. So what's that going to tell us about the moment at that point? Since the shear is going through 0, what's that telling us? When the shear line crosses 0, you're getting a point of maximum moment, okay? A point of maximum moment. So the first moment, if we call that point A, that's just equal to the area of 1. So the area of 1 is going to be 1,200 times 4 feet. That gives us 1,200 times 4 feet. That gives us what? Plus 4,800. Is that what you guys get?
Yep.
And that would be foot-pounds. That's your unit. So what happens here is this, because it's just a rectangular load, what you're getting is just a straight line. So it's just a slope line that starts at 0 and it maxes out like that. And we know that that's at 4,800 positive. So the moment at B, the endpoint has to be 0, right? So that's going to be equal to the area of 1 plus the area of 2. Area of 1 plus area of 2. So area of 1 is 4,800, and then this is going to be plus a minus 800 times 6. If that doesn't give us 0, we've got a problem. 800 times 6 is a negative 4,800. 4,800 plus 4,800 gives us 0. And our moment diagram, again, because that's a straight rectangle load, it's just going to shoot straight down. It's going to just shoot straight down like that, goes to 0. And I got a little piece sticking up, shouldn't be like that. Okay? So where's your point of maximum moment for this diagram? And what's its value? Where's the point of maximum moment and what's its value?
Wouldn't it be 2,000 and 4,800 is value?
Well, just the maximum moment. Not sure. The point of maximum moment is 4,800 foot kips, and it's located 4 feet from the left or 6 feet from the right.
Okay.
So this would be a critical point on that beam. You would not want to put a splice right here because that moment would probably potentially fail that splice, okay?
Yep.
Or you might need some lateral bracing right there to keep it from trying to bend. That's what that's telling you. Are you guys getting the idea?
Yeah.
What about the point of maximum shear?
That would just be A, wouldn't it?
Well, there is no point because it has a range of maximum shear, right? So
Oh, yeah.
it starts at 12, but it actually operates all the way over to 4. So you have a range of maximum shear in this picture, okay? Not a point. Does that make sense now?
Yeah.
Okay. You guys getting the idea?
Yeah, it seems pretty simple.
It is pretty simple, actually. Okay, it is pretty simple. Let me see if I got another. I'm going to try see if I got another nice diagram that we can do. It's not too convoluted. It's hard for me to do them on these pictures. We're going to be able to do these on the board a lot better. But let me try one. Let me see. Let's see if I got one I can do with you. Let's see. I have trying to find. I've got some really good ones here, but I don't want them to be too involved. Okay, I got a nice one. We'll do this one. All right, so let me clean this up. And we're going to start out, we're going to have, give me a sec here. Let me go back to here. And I'm going to start out with a load diagram. So we got a load diagram up here. And that thing's going to have a uniformly distributed load across it. And then it's going to have a concentrated load into reactions, okay? So let me draw these here. Concentrated load, reaction, reaction. Okay, so concentrated load is 4,000 pounds. We know that it is 12 feet from here to here, 6 feet to here, and 4 feet to here. And we know that this guy has a load rate of 100 pounds per foot. And this guy is 4,000 pounds concentrated. I'm just going to go ahead and give you the load rates or the loads for the reactions so that we don't have to go through that. So this turns out to be 3763.6. And this turns out to be 2036.4. Okay, I'm going to give you guys a minute to draw that. I'll be right back. Okay, everybody got that? Who can tell me where my critical lines are?
A.
Okay, calling this A, I guess.
Yeah.
Okay, so yep.
Both edges, A, B, and then 4,000.
So I'm going to grab a one here, right? And then you said over here?
Yep.
And the concentrated load, right?
Yep.
Perfect. You got one more there that you're missing.
Would it just be in the middle of the 150 foot or pound per foot?
It would not. It would be either to the left or the right, where it starts or begins, ends. So I'm going to put one here too.
Okay.
Okay. So you always, if you start, I don't think really Tom talks about that in his book, but I'm going to tell you, if you draw those critical lines right away, then it really makes the rest of everything work really smooth, okay? So think about those critical lines. I'm going to now generate for us our graphs for our shear moments. So I'm going to put the moment actually does not drop below 0, so I'm going to be able to put him down here. So I know my moment doesn't drop below 0. He's going to be here, and I'm going to generate my shear. We're going to generate our shear up here.
And how do you know it doesn't drop below 0?
Well, it has to start at 0 and end at 0. I know because my picture does. Okay.
Okay.
It doesn't. That's not always going to be true. I just know that because I'm trying to figure out room to draw this for you guys. Okay. I don't always know that when I start out. The only reason I know that is because I have this pre-worked out. Okay.
Okay.
Yeah. So you don't always know that. That's correct. Okay. So Okay, so this is shear. Whoops. So this is my point of zero shear. This will be my point of zero moment. We're going to do the shear. We're going to develop the shear first, and we're going to develop the moment, okay? So let's change color here. I think that's helpful. All right. So we're going to start over here. We've got a point of shear. Starting point would be what? 2,000. 2,000 straight up, right? Right at that reaction, correct?
Yep.
So that's going to come up like about this. And we're going to call that 2036.4. That's positive. Now what's happening as we step across this beam? Is it staying constant or is it dropping?
Dropping.
It's dropping. It's dropping at a rate of 150 pounds per foot, right?
Yep.
So the shear, we'll call that like to that point A, is going to be equal to your starting shear, which is 2036.4 minus 150 times 12. Let me ask you, could that be positive ever? If this load rate was pushing up, it could, okay? But in this case, we're saying the load rate is going down. So most of the time, you're probably going to see those negatives, okay? But don't just always assume it is, right? So we want 150 times 12. And we're going to subtract that from the 2036.4. You guys let me know what you got. I got a positive 236.4, and that would be pounds. Is anybody getting that number?
Yep, that's what I got.
Okay, so what that's saying is this is diagonally dropping from that point down to, let's say, a point about right there, like that. So notice what's happening as we step across this beam, the shear is diminishing. It's getting towards zero, all right? But it's not going to zero, so we don't have a point of maximum moment anywhere yet, okay? Make sense?
Yep.
So at this point, what's happening between the end of that loading and this concentrated load? Is there any force in there? Is there any force between here and here?
Yeah.
There is?
4,000 pounds.
Well, that's, no, between here and here.
No.
Not at that point, but between here and here. There's nothing, right? So what that indicates to you is that this is going to stay constant at 236.4. So the shear remains constant to that point. Now, when we hit this, it's going to drop. So we're going to get the point B, we're going to have 236.4 minus what? 4,000 pounds, right? And that gives us a negative 3763.6 pounds. You guys seeing that?
Yep.
Is it important that that number came out to be that? Because if it doesn't agree with that, we got a problem, right? So that pretty much validates at this point what we got going on here is that that shear is dropping like a rock at that point. And then it's going to remain constant until you get back to your reaction. And it's going to remain that value of negative 3763.6. And then when you hit that reaction, you're pushing it back up with what? A positive 3763. So that shear at that point, the shear at that point, if you wanted to just call that C arbitrarily, it's going to be 3763.6 minus plus 3763.6. That has to be equal to 0. If it doesn't equal 0, you got a problem. Again, that would tell you you've got a reaction issue, you've got something else going on. Is everybody okay with that on the shear?
Yeah.
Okay, so how many areas do we have to consider? 1, 2, 3. So what that tells us, we're going to have 3 little moments that we're going to calculate essentially. And the other thing that's going to be true here is that the moment is going to peak at some point and then drop back down to 0. Where's it going to peak? You can already tell me where it's going to peak. It has to peak where the shear diagram crosses the 0 line, right here. So it's going to peak at this point. So it's going to go up and then it's going to drop. Okay? So everybody care that?
Yeah.
All right, so let's let me say, so the first moment always has to start at 0 and it has to end at 0, right? That's what that said. Starts at 0, ends at 0. So the moment to this point, which we could call moment at A, and that's just an A arbitrarily, is going to be equal to the area of A. Now what we have here is, what's this kind of guy figure called again? That's a trapezoid, right? So we're going to take this side plus that side. So we've got 2036.4 plus 236.4 divided by 2 times the distance over which it's acting. And that would give me, let's see what we come up with. I get like 13,000. 36.8. That's a plus. Now what that's doing, it's doing it parabolically. I'm not going to be able to draw a parabola very well. I don't think I can. Let me see if it'll, maybe let me do that. Yeah, it's not going to work very well. My things are going to get too close. Anyway, I'll try this later. So basically I've got a parabola that's going to be opening like this. And that point is at 13,636.8 to that point. All right, you guys get that number? The area of A is this side plus that side divided by 2 times this distance of 12. So all I'm doing is calculating the area of that trapezoid. All right?
Yep.
The moment of the peak, which is going to be here, we'll just call that the moment at B, is going to be the area of 1 plus the area of 2. Area of 1 is 13,636.8 plus 236.4 times 6. 236.4 times 6. And so this is going to give me a larger amount of moment, which this actually is going to be the peak. Yeah. 236.4 times 6 plus 13,636.8. I'm getting 15,000. Yeah, let's do that. 15,055.2. And that, of course, would also be foot pounds. That's also a plus. So what happens is, this is not a very good picture. I'm going to see if I can reconstruct this a little bit better. If you have a French curve, like I said, sometimes it's easier to draw these guys. I'm going to redraw that parabola. But that's a straight line right there. And then I'm going to see if I can generate that. Oop. So this is parabolic. And it's parabolic. It's running from there kind of down to that. Well, that was horrible. Let's see if I can do it any. Whoops. I'm going to try it the other direction. Anyway, that's supposed to be a parabola. So then we have the last moment, the moment at C has to be 0. So that's essentially moment at A1 plus area 2 plus area 3. So basically we have 15,055.2. That's the area of 1 plus the area 2. And we're going to add to that. We're going to add to that a negative 3763.6 times the distance here, which is 4. If that doesn't equal 0, we've got a problem. So let's see what we get up there. $763.6 times 4. And that gives me 0. So what this does, this then drops like that. So this should be parabolic up to here, straight line here, peaks at this point. That's your maximum moment, and that would be 15,055.2. So that's your maximum moment. Maximum shear is here. Those would be the things that you're after. Are you guys getting the idea?
Yeah.
Deciding sometimes whether you have a parabola here or not, I'm going to get you guys set up with a little cheat sheet that shows you how to do it. It all depends on what's happening with your shear. If your shear is diagonal, you're going to have a parabola, and it's either going to open that parabola this way or it might come this way. But if they're just straight rectangles, then you just get straight lines. So you're going to have combinations of those kind of things. But the beauty of this whole process is that all of this is done really pretty straightforward for you, and you don't have to mess with much.
Wait, what was the maximum point and maximum shear?
There is no maximum point of shear. There's just a range of maximum shear.
Oh, okay.
Okay. But what you could say is that your shear max is equal to that. But you can't really say exactly where it is. You just know it's between here and here. Okay.
Got it.
But that's still important because we know that that's a point we may have to beef that beam up. Like you could go with a deeper cross section there because the shear is a problem, see? So you could have a deeper cross section here, but less of a cross section here. But then at this point, what you have is maximum moment, see? So kind of at this point, you got both a maximum moment and a maximum shear happening. So that could be a point, again, you don't want to splice this beam at that point because that beam's going to want to try to rip it, and this is going to want to try to fail it by bending it, okay? So this designer can go through these diagrams and analyze exactly what's going on at any point in time, both in terms of shear and moment, just by looking at those diagrams. And you don't have to go through all that other math we did originally. This takes care of all of it, especially dealing with areas. Just remember, moment of this area, that moment is based on that area, that moment is based on that area plus that area, and that moment is based on the sum of those areas. And if it doesn't start at 0 and end at 0, you got a problem. Okay, that's kind of how that works. All right, any questions? No questions? You can think of right now?
Nope.
All right, so there's homework problems that I want you to do for Thursday. So in chapter 11, they're listed here, okay? 11:1 through 11:9, and then you can skip 10, and then we're going to do 11:11 to 11:14. I suggest trying to do as many of those as you can, okay? And we will go through them on Thursday, first thing. I would like you to probably bring in your lab 2s, just see if there's any questions based on that, and also the deck design projects. I certainly want to start looking at that some more too, okay? But we'll concentrate on homework problems of these sections right here. I'll finish up anything out of 9 that we haven't handled, and also 8. And then we'll be gearing up for our test then a week from Thursday, so that'll look like, I guess that's the 12th then, okay? Any questions?
Nope.
All right, I'm going to go ahead and we're done for the day. I'll go ahead and get this formatted, and I'll get this lecture put back up there. If you read those sections on 11:1 through 11:5, that just will reemphasize what we went through. That'll help, okay?
Good.
All right, I will see you guys on Thursday, okay?
All right.
All right, great.
Yeah.
See ya.